Ladies and gentlemen, here we go. All right, so first of all, today is a day where I'm actually not going to do all that much talking. You are going to be doing most of the work today without my direction, okay? So let me just recap for you what we've been doing and what you will be doing today, okay? We have been doing calculations for the past, I don't know, week or so on titrations, okay? 2 classes ago, we saw how to do a titration when you had strong acid plus strong base. Last class, we did calculations when you had a weak acid and a strong base. And we did a very, very long problem, okay, where you did 5 separate calculations for pH, okay? And actually, this is not the slide I wanted. This is the slide I wanted. If we had plotted a graph of all of the 5 different pHs we found, we would end up with a curve that looked something like that, okay? It's still in this S shape, okay? The difference between this curve and the first one that we saw, which was for a strong titration, same shape, but it's shifted up the y-axis a little bit, okay? Tell me, what is the pH at equivalence for a strong titration? 7, okay? Now this graph is not saying the pH at equivalence is always 9 when you have this situation, but it is trying to illustrate the point that the equivalence point, this kind of a titration will always be in the basic range, above 7, okay? Now, one other thing to take note of, okay? If the equivalence point is right here, and to get to the equivalence point, 50 milliliters of base was required to get us there, where is the halfway point? Correct. Whatever that volume is that got you to equivalence, half of that volume, that would be your halfway point. Now, why do we care so much about that? Do you remember the little trick? It's not really a trick, it's just a bit of a time saver if you remember it. What does pH equal at the halfway point? pKa, all right? If you can remember that, that will be, in some cases, a big time saver for you. All right? If they tell you you're at the halfway point and you're given a Ka value, you could, if you wanted to, write out the reaction, do an ice table, but you don't have to. If you remember that, you can solve for pH very, very quickly and move on to the next problem. Okay. So, let us continue on. What you're going to do today is exactly the opposite. You're going to do, instead of weak acid, strong base, you're going to do weak base, strong acid, and I'm not going to direct you through it. Okay? You're going to do it. Now, just to recap with you, when you're doing a titration where one part is weak, and by the way, I said this last class, you will never have to do math for a titration of weak. You'll either have strong, or weak, strong, or strong, weak. All right? If something weak is part of your titration, we said this last class, let's review it. There are 3 possible scenarios that you will see. Okay? You do a Newman problem. You complete your ice table. At the end of that ice table, here is scenario number 1. You are left with a buffer. How do you find the pH of a buffer? Hendy-Haas, okay? Use the Hendy-Haas equation. That is situation number 1. Situation number 2. And if you go back and look at your notes from last class, that long problem, you will see all 3 of these scenarios. Scenario number 2. You get to the end of your Newman ice table and you are left with only one thing on the product side. And guys, that only occurs at the equivalence point, by the way. What do you do in that circumstance? Do you remember? Switch the reaction and do what kind of a problem? A Wommack's problem. Okay? So, number 1, buffer, use Hendy-Haas. Number 2, you're left with one product and you Wommack's it. The last situation, you're left with 2 things at the end of your ice table, but it's not a buffer, it's 2 of the same type of thing. In the problem we did last class, we were left with 2 bases. What do you do in that situation? Go with the stronger one and ignore the other one, okay? If any of you are concerned with how are you going to know which one is the stronger one, this third scenario where you're left with 2 of the same type of thing, could be 2 bases, could be 2 acids. One of them is always going to be your king daddy, okay? If it's 2 acids, one of them is going to be H+. That's no contest as to which one is stronger. If it's 2 bases, one of your bases is always going to be OH-. Okay? So, you're going to do a problem very similar to what you did last class, except it's going to go a lot faster because I'm not talking through the whole thing. Okay? I'm the one that slows us down here. You're going to go through the steps. And you're going to see the same 3 scenarios that we saw last class, just in a slightly different situation. Okay? Here is your goal. Okay? Am I going to put up the answers? Yes, of course. But your goal is to stay one step ahead of me. Okay? I'm going to wait a while before I start writing up the work. So once I start writing up the work for this first section, you should be on the next one already. Okay? I'm going to walk around and I'm going to help you. This is the true test. Do you know what you're doing or don't you? Okay? Get to it. again, let me say this. I told you this last class. I want you to hear it again. Are you ever going to be asked to do all of this in one problem? No. They're going to focus on one of these additions, okay? Why did I make you do all this? Because there are so many different situations. I wanted to expose you to all of them so that you would know what to do. Okay, to wrap this up, if we had graphed the problem we just did, this is the kind of curve we would see. The pH was slowly falling. All right? We saw an equivalence point below 7 because it was strong acid plus weak base. Remember, guys, that you could see a multiple choice question that wouldn't ask you to do any of the calculations we just did, but they could give you a titration, tell you what the acid is, what the base is, and ask you what the pH at equivalence would be. You don't need to calculate it. What they're trying to test you on is, do you know what range it should fall in? If the question involves a weak base and a strong acid, you are looking for what should be the one and only answer, below 7. Okay? If it was strong, what kind of a pH are you looking for? 7. If it's strong base, weak acid, what are you looking for? A pH above 7. Okay? Where would the halfway point be on this graph? Yeah, 25, so this dot right here, that would be your halfway point where the pH equals pKa. Okay, now, if you would please, in your textbook, go to page 715, 715. Ladies and gentlemen, this very colorful diagram has a list of what are called indicators on it. Okay? Ladies and gentlemen, indicators are used when you actually physically do a titration in the lab, and they are used to tell us when we have reached the equivalence point. Now, why are these necessary? Well, first of all, guys, at some point we will get to do a real titration. And when you do a titration, usually something about your acid and your base is unknown. Typically, it's a molarity. You know the molarity of, let's say, the acid, but you don't know the molarity of the base. And the problem is, okay, well, first of all, the goal of a titration, if you don't know something about one of the pieces, your goal is to get to the equivalence point. But here's the problem. Most solutions in chemistry are clear liquids. How are you supposed to know when you've reached the equivalence point? You need a visual clue. And that is what indicators help us with. They give us a visual indication that we have reached the equivalence point. Now, how do they do that? Well, first of all, okay, this IN right here, guys, I am not meaning the element indium. Okay? I'm using IN to stand for indicator. You need to know that indicators themselves are weak acids. Okay? They're weak acids. They don't dissociate much, but they do dissociate a little bit. Okay? And when they're in certain environments, they are compounds that show a color. Okay? There are not many compounds on Earth that have a color. Most are clear. But indicators are things that have color to them. Now, what's going to determine what color it is? The pH of the environment that it's in. Let us imagine that I have some kind of an indicator and I put strong acid into it. Okay? So I've mixed my indicator with some strong acid. Do strong acids release a lot or a little H plus ions? A lot. Okay? Let's think about Le Chatelier's principle. Shift left, shift right, whatever. Putting an indicator in with a very strong acid, okay, or really any acid for that point, is going to be like adding more H plus. If you add more of a product, which way will this equilibrium shift? Towards the reactants, to the left, okay? That means if this indicator is put in an acidic environment, it will be red in color. If it's in a basic environment, it will be yellow in color, okay? So these indicators that are weak acids themselves, when they're in their acidic form, are one color. And when they're in their conjugate base form, they are a different color. Okay? Well, again, the position of this equilibrium is controlled by the pH of its environment. Okay? I want you to know this term. Okay? Endpoint just means the point in the titration when the indicator changes color. Okay? It's not the same thing as equivalence point, but if you pass the endpoint, you have already also passed the equivalence point. Okay, endpoint just means when the indicator changes color. All right. Now let's talk about how do you know at what pH an indicator is going to change color, because they don't change color all at the same place. Tell me this, guys. If we are doing a titration, and as we go along in the titration, the pH is going up, what must I be adding more and more of in this titration? I must be adding more and more base. Okay? There is some mathematical explanation here. I'm going to just sort of buzz through this and get to what's really important. If you are titrating up, which means I must be adding more and more base, the pH or the indicator will change color at a pH of pKa minus 1. Now, what does that mean? Well, remember that I said indicators are themselves weak acids. So they themselves have a Ka value. And I'm going to give you an example of an indicator that we are going to use at some point. It has a very long name. Maybe you've used it before. Phenolphthalein. Try putting an F and a TH sound right next to each other. It's actually easier to say if you have a lisp. Okay? Phenolphthalein. Okay? Anyway, this is an example of an indicator that we are going to use. And I'm going to tell you, that's not its exact Ka, but that's pretty close. Okay? Remember, indicators are acids, weak acids, so they must have Ka values. If phenolphthalein has a Ka value of 1 times 10 to the negative 9th, could you please tell me what its pKa value is? 9. 9. It's 9, okay? If this is the Ka, when you take the negative log of this number, you will get the number 9, okay? What's 9 minus 1? 8, okay? So ladies and gentlemen, if I'm doing a titration where I'm adding more and more base, and I put phenolphthalein in as my indicator, it is going to change color, and phenolphthalein goes from a clearish white color to bright, bright, bright pink. Okay? When you pass 9 minus 1. When you pass a pH of 8, boom, it turns pink. It's not a gradual change, folks. It's like clear 1 second, and then you add one more drop of base, and boom, it's pink. Okay? So what if you're not titrating up? What if you're titrating down? Which means I must be adding progressively more and more what? Acid. If you're titrating down, the indicator changes color at pKa plus 1. What was our pKa value again? 9. What's 9 plus 1? 10. Okay? Ladies and gentlemen, here is the most important thing on this slide, what's in green. Indicators have what is called a useful range. pKa plus or minus 1. For my example of phenolphthalein, 9 plus or minus 1, that means from a pH of 8 to 10. Now let me tie this all together. Let me go back to telling you what the purpose of an indicator is. Purpose of an indicator is to change color, to tell us when we have passed the equivalence point. Would you please go back and look at that long problem that we did at the beginning of class today? What was the pH at the equivalence point? Okay, 5.22. Does that fall in this range? No. That means phenolphthalein would be a poor choice for an indicator for that particular titration. This is an indicator I would choose if I know that my pH at equivalence is somewhere within this range. Yes, you would. You're absolutely right. You would have to know the Ka of that indicator. Okay? So, if you would please, I want you to now look at this beautiful, colorful chart in your book. Folks, we've got pH values across the top. You have a whole bunch of indicators listed here. These bands are indicating their useful ranges. And not only that, it's telling you their colors as well. For example, hold on. Like bromcresol green. When it's in its acidic form, it is bright yellow. When it's in its basic form, it is bright blue. Notice I didn't say when it's in the acidic range. I said when the indicator is in its acidic form. Because, do you all agree? Look at the end of this band. pH of about 5.4 or so. Isn't that in the acidic range?
Yes.
Yeah, but it's not going to be yellow, it's going to be blue. It means bromcresol green will be yellow when it's below a pH of about, 4.6, and it will be blue when it's above a pH of 4.6. So please tell me, guys, going back to the problem we did at the beginning of beginning of class today, which indicator, or if there's more than one, which would be a good one to choose for this titration we did in class today? Okay, bromcresol green. What else could you use?
Methyl red.
You could use methyl red. You could probably get away with using Areochrome black tea. All right. The best choice of those three is methyl red. Okay. Anybody want to tell me why?
Because it falls in the middle of those.
Exactly. You are looking for an indicator where the pH at equivalence is as close to the middle of its band as you can get. Correct. You can't, Let me give you an example of what a test question would look like. And guys, I can almost guarantee that you're going to see a question like this. They do this every year. Okay. Let's say you're in free response. Okay, you were not asked to do this entire problem, but you were told to do the calculation just at the equivalence point. So just at the 50 milliliter addition, okay? You found a pH. Maybe that was part A of the question. Part B gives you 3 choices for indicators and says which indicator is the best choice. Maybe they give you a chart like this, or they could give you, indicators A, B, and C, but they give you their Ka values. Okay. Could you pick which one to use? Okay. pKa, figure out what the useful range is for each one. And guys, usually they will say, which indicator is the appropriate one? Explain your answer. Okay. If the pH at equivalence, let's say, falls in the range of indicator B, and I say, okay, that's the one I'm going to choose. The explanation would be the pH at equivalence falls within the useful range of indicator B. Do you want me to say that again? You got it? I'll say it one more time. Let's say I chose indicator B and it says explain why you chose what you chose. The pH at equivalence falls within the useful range of indicator B. Why are there some indicators that have 2 areas of useful range? Let me give you a hint. Remember that I said that indicators are just weak acids. Okay? These bands are where we see the change from the acid form to the conjugate base form. What's our definition of an acid from long ago? What is this? What's an acid? Not where is the pH range. What does an acid do? They give away a hydrogen. What if they have 2 hydrogens to give up? A diprotic acid? How about carbonic acid? H2CO3? That's a weak acid that's diprotic. This is a diprotic indicator. So is this one. So is this one. They have 2 areas of useful range. Okay? Question? Yes, you would. Yes, you would. Yep, they would have a Ka1 and a Ka2, 2 separate Ka values.